We are taught to view the natural world through divided lenses. You study biology to understand cells, chemistry to understand molecules, and physics to understand motion, treating each discipline as an entirely separate system running on its own distinct rulebook. But follow those rules down to the smallest possible scale, and you hit a ceiling. Thanks to physicists like Niels Bohr and the Copenhagen interpretation, we accept that at the quantum level, the absolute laws of reality dissolve into pure probability. This creates severe technical limitations. Because we treat the foundational layer of reality as random, our attempts to build quantum computers are incredibly fragile and prone to error. In biology, we're forced to rely on models that assume cellular reactions happen by sheer chance, rather than structural certainty. It leaves us with a glaring paradox. If the macro world of living organisms and orbiting planets is highly ordered and predictable, why do we assume the microscopic foundation holding it all together is built on a chaotic game of chance? Researcher Pravir Malik offers a radical counter-hypothesis. The universe is a single, fully integrated system, and the rules of the macro world apply all the way down to the quantum floor. He calls this approach reverse extrapolation. The idea is that decoding the invisible bottom of reality doesn't require smashing particles in a void. Instead, we can read the quantum level by looking at the visible structures built on top of it. Identifying these recurring symmetries across physical scales provides a structural bridge to the quantum level, one that bypasses isolation and looks for the logic hidden in plain sight. This animated diagram illustrates how that pattern emerges. Look at any living biological cell. It is animated by exactly 4 distinct structural categories: proteins, polysaccharides, nucleic acids, and lipids. Step down to the chemical level. That exact same 4-part division governs all elements in the periodic table, grouping them strictly into the S, P, D, and F atomic shells. Step down again to the physical level. The symmetry persists subatomically in the standard model, organizing reality into exactly 4 particle categories: quarks, leptons, bosons, and the Higgs field. Malik deduced that this recurring symmetry implies a single 4-fold root code operating at the quantum level. He defines these 4 dimensions as presence, power, knowledge, and harmony. These 4-part symmetries suggest that the macro world is not merely a byproduct of microscale chance. Instead, the same organizational logic found in cells and atoms appears to emerge from a singular fractal blueprint at the quantum root. This theory, known as the quaternary interpretation of quantum dynamics, or QIQD, is currently being used as the foundation for an entirely new computing architecture. Malik translated this theoretical fractal code into a rigid physical law suite. It consists of 23 specific laws and mathematical seeds that dictate how energy materializes into form. This flowchart shows how the QIQD dialogical computer actually operates. It uses the natural language abilities of modern large language models to accept human intent, filters that text through the 23 physical laws, and outputs the result as structured mathematical commands. By formalizing these universal laws into code, AI allows us to move beyond passive observation. We can now treat physical reality as a system for which we can write deterministic software. To test this, researchers created a highly specific simulation, forcing cellular mitochondria to increase their production of ATP, the currency of cellular energy. Classical biology treats this as a stochastic process. When a cell faces oxygen starvation, known as hypoxia, traditional models rely on probability, hoping random chemical reactions will eventually restore the energy flow. This visualization shows the QIQD alternative. The dialogic computer deploys an electromagnetic seed, a precise 4-frequency pulse. By perfectly aligning and locking into the physical architecture of the mitochondria, it predictably reconfigures the cellular environment from the quantum level up. Treating biology as programmable code allows us to move past the limitations of chemical guesswork, aiming for the same deterministic reproducibility found in traditional software engineering. We are moving away from a scientific model reliant on random chance and entering a framework of qualified determinism. Almost a century ago, Albert Einstein famously rejected the randomness of the Copenhagen interpretation, stating that God does not play dice. This structural approach finally validates his intuition. Malik's model frames the universe as a highly ordered system running on a readable codebase, a far cry from the probabilistic chaos once thought to govern the microworld. Today, this process operates entirely in AI-driven dialogic simulations. The immediate next step is running these physical laws through high-performance numerical computing models. Long-term, the roadmap points to physical QIQD hardware. We're looking at nanoscale cyborgs capable of synthesizing room-temperature superconductors or directly maintaining human cellular life from the bottom up. This technological roadmap suggests that intelligence is baked directly into the fabric of spacetime, and with QIQD, we finally possess the dictionary to speak its language.